B1 plus B2, rho 1 plus rho 2, and J1 plus J2 is also a solution. So that's the meaning, the technical meaning of linearity. We have two solutions, we can add them. We have a single solution, you can scale it by a number. Now, I have not shown you the equations and what makes them linear, but I can explain this a little more as to what does it mean to have a linear equation. Precisely, what do we mean by a linear equation? So a linear equation, and we write it schematically. We try to avoid details. We try to get across the concept. A linear equation, we write this L u equal 0, where u is your unknown, and L is what is called the linear operator. Something that acts on u. And that thing, the equation, is of the form L on u equals 0. Now, you might say, okay, that already looks to me a little strange because you have just one unknown, and here we have several unknowns. So this is not very general. And you could have several equations. Well, that won't change much. We can have several linear operators if you have several equations, like L1 on something, L2 on something, all these ones equal to 0, as you have several equations, or you can have several u's or several unknowns, and you could say something like you have L on u, v, w equals 0, where you have several unknowns. But it's easier to just think of this first, and once you understand this, you can think about the case where you have many equations. So what is a linear equation? It's something in which this L, the unknown can be anything, but L must have important properties. As being a linear operator will mean that L on A times U, where A is a number, should be equal to A LU, and L on U1 plus U2 on two unknowns is equal to LU1 plus LU2. This is what we mean by the operator being linear. So, if an operator is linear, you also have L on alpha U1 plus beta U2. You apply first the second property, L on the first plus L on the second. So this is L of alpha U1 plus L of beta U2. And then using the first property, this is alpha L of U1 plus beta L of U2. And then you realize that if U1 and U2 are solutions, which means LU1 equal LU2 equals 0, if they solve the equation, then alpha U1 plus beta U2 is a solution. Because if LU1 is 0 and LU2 is 0, L of alpha U1 plus beta U2 is 0, and it is a solution. So this is how we write a linear equation. Now, an example probably would help. if I have the differential equation du dt plus 1 over tau u equals 0, I can write it as an equation of the form Lu equals 0 by taking L on u to be defined to be du dt plus 1 over tau u. Now, it's pretty much, I haven't done much here. I've just said, look, let's define L acting on u to be this, and then certainly this equation is just Lu equals 0. The question would be maybe if somebody would tell you, how do you write L alone? Well, L alone, probably we should write it as d dt without anything here, plus 1 over tau. Now, that's a way you would write it to try to understand yourself what's going on. And you say, well, then when L acts on the variable u, the first term takes the derivative, and the second term, which is a number, just multiplies it. So you could write L as this thing. And now it is straightforward to check that this is a linear operator. L is linear. And for that, you have to check the two properties there. So for example, L on AU would be d dt of AU plus 1 over tau AU, which is A times du d tau plus 1 over tau u, which is ALU. And you can check, I asked you to check the other property. L on u1 plus u2 is equal LU1 plus LU2. Please do it. So here is something funny. You might say, okay, what is simpler, a theory that is linear or a theory that is not linear? And the answer, of course, a linear theory is much simpler. Maxwell's equations are linear. Einstein's theory of relativity is very nonlinear, very complicated. How about classical mechanics? Is classical mechanics linear or nonlinear? What do we think? Can't hear anyone. Linear, okay. You may think it's linear, but because it's supposed to be simple, but it's not. It's actually very nonlinear. Newton could solve the two-body determinism. And it all begins with photons. Einstein reluctantly came up with the idea that light was made of quanta of light called photons. Now, when you think of photons, we think of a particle. So everybody knew that light was a wave. Maxwell's equations have been so successful. Nevertheless, photoelectric effect, Planck's work, all were leading to the idea that in some ways, photons were also particles. For photons, or light. So when you think of a particle, however, there's a kind of an important difference between a particle in the sense of Newton, which is an object with zero size that carries energy, that has a precise position and velocity at any time, and the quantum mechanical idea of particle, which is just some indivisible amount of energy or momentum that propagates. So light was made of photons called packets of energy. And a photon is a particle, a quantum mechanical particle, not in the sense that maybe has position and velocity determined or is a point particle, but it's more like a packet that is indivisible. You cannot decompose it in further packets. So Einstein realized that for a photon, the energy was given by h nu, where nu is the frequency of the light that this photon is helping build up. So if you have a beam of light, you should think as billions of photons, and according to the frequency of that light that is related to the wavelength by the equation frequency times wavelength is velocity of light. You typically know for light the wavelength, and you know the frequency, and then you know the energy of each of the photons. The photons have very, very little energy. They have very, very little energy, but your eyes are very good detectors of photons. If you're in a totally dark room, your eye probably can detect as little as 5 photons if they hit your retina. So it's a pretty good detector of photons. Anyway, the thing that I want to explain here is what happens if a beam of light hits a polarizer. So what is a polarizer? It's a sheet of plastic or some material that has a preferential direction. Let me align that preferential direction with the x-axis. And that's a polarizer. And if I send light that is linearly polarized along the x-axis, it all goes through. If I send light linearly polarized along the y-axis, nothing goes through. It all gets absorbed. That's what a polarizer does for a living. In fact, if you send light in this direction, the light that comes out is identical to the light that came in. The frequency doesn't change, the wavelength doesn't change. It's the same light, the same energy. So far, so good. Now let's imagine that we send in light linearly polarized at some angle alpha. So we send an electric field E alpha, which is E0 cosine alpha x hat plus E0 sine alpha y hat. Well, you've studied electromagnetism, and you know that this thing basically will come around and say, okay, you can go through because you're aligning in the right direction, but you're orthogonal to my preferential direction. Orthogonal I absorb, so this disappears. So after the polarizer, E is just E0 cosine alpha x hat. That's all that is left after the polarizer. Well, here is something interesting. You know that the energy on an electromagnetic field is proportional to the magnitude of the electric field square. That's what it is. So the magnitude of this electric field, if you can notice, it's the square root of the sum of the squares will give you E naught as the magnitude of this full electric field. But this electric field has magnitude E naught cosine alpha. So the fraction of power, of energy through is cosine alpha squared. The energy is always proportional to the square, so the square of this is E naught squared cosine squared alpha, And for this one, the magnitude of it is E naught, so you divide by E naught, and cosine alpha is the right thing. This is the fraction of the energy. If alpha is equal to 0, you get cosine of 0, 1. You get all the energy, 1. If alpha is equal to pi over 2, the light is polarized along the y direction, nothing goes through. Indeed, cosine of pi over 2 is 0, and nothing goes through. So the fraction of energy that goes through is cosine squared alpha. But now, think what this means for photons. What it means for photons is something extraordinarily strange, and so strange that it's almost unbelievable that we get so easily in trouble. Here is this light beam over here, and it's made up of photons. All identical photons, maybe billions of photons, but all identical. And now think of sending this light beam over there, a billion identical photons, you send them one by one into this thing and see what happens. You know what has to happen because classical behavior is about right. This fraction of the photons must go through, and 1 minus that must not go through. You see, it cannot be that comes a photon and half of it goes through, because there's no such thing as half of it. If there would be half of it, it would have half the energy, and therefore different color, and we know that after a polarizer, the color doesn't change. So here is the situation. You're sending a billion photons, and say 1/3 has to get through. But now the photons are identical. How can that happen? In classical physics, if you send identical photons, whatever happens to a photon will happen to all. But the photon either gets absorbed or goes through. And if it gets absorbed, then all should get absorbed. And if it goes through, all should go through because they're all identical. And now you have finally a situation in which an identical set of experiments with identically prepared objects sometimes give you different results. It's a debacle. It's a total disaster what seems to have happened here. You suddenly have identical photons, and sometimes they go through, and sometimes they don't go through. And therefore, you've lost predictability. It's so simple to show that if photons exist, you lose predictability. And that's what drove Einstein crazy. He knew when he introduced photons that he was getting in trouble. He was going to get in trouble with classical physics. So, possible ways out. People speculated about it. People said, well, yes, the photons are identical, but the polarizer has substructure. If it hits in this interatomic part, it goes through, and in that interatomic part, it doesn't go through. People did the experiment many times. It's not true. The polarizer is like that. And then came a more outrageous proposition by Einstein and others, that there are hidden variables. You thought the photons are identical, but you think they are identical, but a photon has a hidden variable, a property you don't know about. If you knew that property about the photon, you would be able to tell if it goes through or it doesn't go through, but you don't know it. So that's why you're stuck with probabilities. It's because the quantum theory is not complete. There are hidden variables, and once you put the hidden variables, you'll discover the photon has more something inside it, and they are not the same, even though they look the same. And that's a hidden variable theory. And it sounds so philosophical that you would think, well, if you don't know about them, but they are there, these properties, how could you ever know they are there? And the great progress of John Bell with the Bell inequalities is that he demonstrated that that would not fix the problem. Quantum mechanics cannot be made deterministic with hidden variables. It was an unbelievable result, the result of John Bell. So that's something we will advance towards in this course, but not quite get there. 805 discusses this subject in detail. So at the end of the day, we've lost determinism. We can only predict probabilities. So photons either gets through or not, and can only predict probabilities. Now, we write in classical physics a beam like that, but how do we write the wave function of a photon? Well, this is quite interesting. We think of states of a particle as wave functions, and I will call them sometimes states. I will call them sometimes wave functions, and I sometimes will call them vectors. Why vectors? Because the main thing you do with vectors is adding them or multiplying them by numbers to scale them. And that's exactly what you can do with a linear equation. So that's why people think of states or wave functions as vectors. So, and Dirac invented a notation in which to describe a photon polarized in the x direction, you would simply write something like this. Photon, colon, x, and this object. You think of it as some vector or wave function, and it represents a photon in the x direction. And we're not saying yet what kind of vector this is, but it's some sort of vector. It's not just a symbol, it represents a vector, and that's a possible state. This is a photon polarized along x. And you can also have, if you wish, a photon polarized along y. And linearity means that if those photons can exist, the superposition can exist. So there can exist a state called cos alpha photon x plus sine alpha photon y, in which I've superposed one state with another, created a sum, and this I call the photon state polarized in the alpha direction. So this is how in quantum mechanics you think of these photons. We will elaborate that. Compare with this equation. It's kind of interesting. What you lose here is this ease. There's no ease there because it's one photon. When you have a big electric field, I don't know how many photons there are. I would have to calculate the energy of this beam and find the frequency that I didn't specify and see how many photons. But each photon in this beam, quantum mechanically can be represented as this superposition. And we'll talk more about this superposition now because our next subject is superpositions and how unusual they are. Well, the hidden variable explanation failed because Bell was very clever and he noted that you could design an experiment in which the hidden variables would imply that some measurements would satisfy an inequality. If there existed hidden variables and the world was, after all, classical, the results of experiments would satisfy a Bell inequality. And then a few years later, the technology was good enough that people could test the Bell inequality with an experiment. And they figure out it didn't hold. So The hidden variables lead to Bell inequalities that are experimentally shown not to hold. And we will touch a little bit on it when we get to entanglement. After the polarizer, the photon is in the state photon X. It's always polarized along the X direction. So it's kind of similar that this doesn't go through, this goes through, but at the end of the day, as we will explain very soon, the cosine alpha is not relevant here. When it goes through, the whole photon goes through. So there's no need for a cosine alpha. So that's what goes out of the polarizer. Superposition is very unusual and very interesting. Now, we've said about superposition that in classical physics, when we talk about superposition, we have electric fields, and you add the electric fields, and the total electric field is the sum of electric fields, and it's an electric field, and there's nothing strange about it. The nature of superposition in quantum mechanics is very strange. So, of superposition. I will illustrate it in a couple of different ways. One way is with a device that we will get accustomed to it. It's called the Mach-Zehnder interferometer, which is a device with a beam splitter in here. You send in a beam of light input, beam splitter, and then the light, indeed, half of it gets reflected, half of it gets transmitted. Then you put a mirror here, mirror 1, you put a mirror 2 here, and this gets recombined into another beam splitter. And then, you know, if there would be just a light going in here, there would be two things going out. There's another one coming from the bottom. There will be two. There will be interference. So you put a detector D0 here and a detector D1 here to detect the light. So that's the sketch of the Mach-Zehnder interferometer, beam splitters and mirrors. Take a beam, split the light, go down, up, and then recombine it and go into detectors. You can get, and this is was invented by these two people independently, 1890s. 91 to 92, apparently. And people did this with light, beams of light, before they realized they're photons. And what happens with a beam of light, it's interesting, you know, comes a beam of light, the beam splitter sends half of the light one way, half of the light the other way. You already know with quantum mechanics that's going to be probabilistic. Some photons will go up, maybe some photons will go down, or something more strange can happen. If you have a superposition, some photons may go both up and down. So that's what can happen in quantum mechanics. We can get, if you send a beam, classical physics, it divides half and half and then combines, and there's an interference effect here. And we will design this interferometer in such a way that sometimes we can produce an interference that everything goes to D0, or everything goes to D1, or we can produce suitable interferences that we can get fractions of the power going into D1 and D2, D0 and D1. So we can do it in different ways, but we should think of this as a single photons going one at a time. You see, whatever light you put in here, experimentally, the same frequency goes out here. So what is interference? You might think intuitively that interference is one photon interfering with another one, but it can't be. If two photons would interfere in a canceling, destructive interference, you would have a bunch of energy that goes into nothing. It's impossible. If they would interfere constructively, you would add the electric fields and the amplitude would be 4 times as big because it's proportional to the square. So, but 2 photons are not going to go to 4 photons, cannot conserve energy. So first of all, when you get light interference, each photon is interfering with itself. It sounds crazy, but it's the only possibility. They cannot interfere with each other. You can send the photons one at a time. And therefore, each photon will have to be in both beams at the same time. And then each photon, as it goes along, there will be an interference effect, and the photon may end up here or end up there in a probabilistic way. So you have an example of superposition, a single photon state, a single photon is equal to superposition of a photon in the upper beam and a photon in the lower beam. It's like 2 different states, a little different from here. You had photons in 2 different polarization states superposed. Here you have photons in 2 different beams. A single photon is in both beams at the same time. And unless you have that, you cannot get a superposition and an interference that is consistent with the experiment. So what does that mean for superpositions? Well, it means something that we can discuss, and I can say things that at this moment may not make too much sense, but would be a good idea that you think about them a little bit. We associated states with vectors. States and vectors are the same thing. And it so happens that when you have vectors, you can write them as the sum of other vectors. So the sum of these 2 vectors may be this vector. But you can also write it as the sum of these 2 vectors. These 2 vectors add to this thing. And you can write any vector as a sum of different vectors. And that's actually quite relevant. You will be doing that during the semester, writing a state, a superposition of different things. And in that way, you will understand the physics of those states. So, for example, we can think of 2 states, A and B. And you see, as I said, states, wave functions, vectors, we're all calling them the same thing. If you have a superposition of the states A and B, what can happen? All right, we'll do it the following way. Let's assume if you measure some property on A, you always get value A. So you measure something, position, momentum, angular momentum, spin, energy, something. On A is a state that you always get A. Suppose you measure the same property on B, you always get B as the value. And now, suppose you have a quantum mechanical state, and the state is alpha A plus beta B. It's a superposition. This is your state. You superimpose A and B. And now you measure that property. That same property you could measure here, you measure it in your state. The question is, what will you get? You've now superposed those states. On the first state, you always get A. On the second state, you always get B. What do you get on the superposed states where alpha and beta are numbers? Complex numbers in general. Well, the most perhaps immediate guess is that you would get something in between, maybe alpha A plus beta B, or an average or something. But no, that's not what happens in quantum mechanics. In quantum mechanics, you always get A or you always get B. So you can do the experiment many times and you will get A many times and you may get B many times, but you never get something intermediate. So this is very different than in classical physics. If a wave has some amplitude and you add another wave of different amplitude, you measure the energy, you get something intermediate. Here not. You make the superposition, and as you measure, you will either get the little a or the little b, but with different probabilities. So roughly speaking, the probability to get little a is proportional to the number in front of here is alpha squared, and the probability to measure little b is proportional to beta squared. So in a quantum superposition, a single measurement doesn't yield an average result or an intermediate result. It leads one or the other. And this should connect with this. Think of the photon we were talking before. If you think of the photon that was at an angle alpha in this way, you could say that the polarizer is measuring the polarization of the object. And therefore, what is the possible result? It may measure the polarization and say, oh, if it's in the x direction, you get it right. And what is the probability that you get it to be in the x direction is proportional to cosine squared alpha, the coefficient here squared. So the probability that you find the photon after measuring in the x direction is cosine squared alpha, and the probability that you'll find it here is sine squared alpha. And after you measure, you get this state, which is to say the following thing. The probability to get the value A is alpha squared, but if you get A, the state becomes A because this whole state of the system becomes that. Because successive measurements will keep giving you the value A. If you get B, the state becomes B. So this is what is called the postulate of measurement and the nature of superposition. This is perhaps the most sophisticated idea we've discussed today, in which in a quantum superposition, the results are not intermediate. So when you want to figure out what state you have to prepare many copies of your state in this quantum system and do the experiment many times, because sometimes you'll get A, sometimes you'll get B. After you've measured many times, you can assess the probabilities and reconstruct the state. We spoke about superposition, and we showed how when you have two states that are superimposed, the resulting state that is built up doesn't have properties that are intermediate between the two states that you're superimposing, but rather, when you do a measurement, you obtain the result that you would sometimes obtain the result that you would have with one of the states, and some other times with different probabilities, the results as if you had the other state. So it's a strange kind of way in which things are combined in quantum mechanics. So the next thing we have to say is a physical assumption that is made here, and it is that if you have a state and you superimpose it to itself, you haven't done anything. So the superposition of a state with itself has no physical import. So we can say this, it's a physical assumption, superimposing a state to itself does not change the physics. So if I have a state A, this is physically equivalent, I'll write physically equivalent with this symbol, to the state A plus A, which would be 2 times A. It's physically equivalent to the state minus A. It's physically equivalent to the state IA on anything. It's not equivalent to 0A, because that would be the 0 state. So it's physically equivalent as long as you have a non-zero coefficient. All these states are supposed to be physically equivalent. And that will eventually mean that we sometimes choose a particular one in those collection of states that is one that is convenient to work with, and that will be called a normalized state. A state that satisfies other properties having to do with the norm squared of the state. That will come later, but it's important that the number that is multiplying the physical state of your system has no relevance. And you could say, well, why all of a sudden you tell us this? Could this be shown to be necessary, or it's a physical assumption? So can we test it? Does it make some sense? And we can make some sense of this assumption at this level. And we do it with states of light. So remember, we spoke about photons hitting a polarizer, and we could speak of two independent kinds of photons. Photons polarized along the x-axis, and a photon polarized along the y-axis. And those are two quantum mechanical states. Now, suppose I decide to superpose those states to create the most general photon state. I would have an alpha, which is a number here, a complex number, and a beta there. And I would say, okay, here is my most general photon states, And how many parameters does this state have? It has two complex parameters, alpha and beta, and therefore 4 real parameters. And then you think about polarization states, how many parameters they have. And as we'll review in a second, it's well known that photons, their polarization state can be expressed with just 2 real parameters. So some counting is not going very well here. But here comes the help. If the overall coefficient here doesn't matter, if I can change it, I can multiply everything by 1 over alpha, and therefore get that the state is just the same, physically equivalent to this state, beta over alpha, photon, y. So all the physics is contained in this state as well. And if all the physics is contained in that state, I must look how many parameters it has. It still looks like there's 2 numbers here, but only the ratio appears. So if you call beta over alpha the number gamma, it's just 1 complex parameter. And therefore, thanks to this assumption, you now get that the most general photon polarization state has just 1 complex parameter, or just equivalently 2 real parameters. And that is the correct number. Indeed, if you have a polarization, a wave that has some polarization, the most general polarization state of a wave is an elliptical polarization. You probably did study a lot about circular polarizations. Maybe you also heard about the elliptical one, in which the electric field in a circular polarization, the electric field at any point traces a circle. But if you have an elliptical polarization, the electric field traces an ellipse. And that ellipse has an angle that is 1 parameter, and for an ellipse, the other, since the size doesn't matter, the size depends just on the magnitude of the electric field. It's not a parameter of the polarization of the wave. Since the size doesn't matter, it's the shape of the ellipse that matters, and that's characterized by the eccentricity or by the ratio A over B of the semi-major axis, so parameters. 2 parameters, and they are A over B and theta. So an elliptically polarized wave, which is the most general state of polarization of a wave, has 2 real parameters, and now, thanks to this physical assumption, we get this right. And this is important because that's something we're going to use all the time, that the overall factor in a wave function does not matter. So if we have superpositions, I want to emphasize one more thing about superpositions. And for that, I'm going to use spins. So what is spin? Spin is a property of elementary particles that says that actually, even if they're not rotating around some other particle, they have angular momentum. They have intrinsic angular momentum, as if they would be made of a tiny little ball that is spinning. I say as if, because nobody has ever constructed a model of an elementary particle where you can really make it spin and calculate how it works. Somehow this elementary particle has angular momentum, is born. Even if it is a point particle, it has angular momentum, and it's a spin. And spin is very quantum mechanical, and we can't quite understand it without it. So what happens is that you can measure the spin of a particle, and then if you measure it, you have to decide, however, since angular momentum is a vector, what direction you should use. And suppose you use the z direction to measure the spin of a particle, you may find that the particle has either spin up or the particle has spin down. Spin. And the spin is the direction of the angular momentum. And that's the funny thing that happens with most matter particles. These are spin 1/2 particles. The spin can be up or can be down along the z direction that you measure. You measure it, and you never find it's 0 or a little bit. It's just either up with the full magnitude or down with the full magnitude. That is a spin 1/2 particle. And the state where it is up, we sometimes denote it with an arrow up and colon z, because it's up along z. And this would be down, an arrow down along z. But if those are possible quantum states, you could build a new quantum state by superposition, which would be up along z plus down along z. Now, if I wish to normalize it, I would put a factor in front of this. I will not talk about normalizations at this moment. They're not so important. If you are faced with this quantum state, so suppose you have an electron that is not in this state nor in this state, but is in this state, in a quantum superposition. So you go and you decide to try to measure it. Now, since you cannot predict what an electron is going to be doing, we cannot predict things in quantum mechanics with certainty, we, since we're going to do this experiment, avail ourselves of 1,000 copies of this electron. All of them in this peculiar quantum state. So you have the 1,000 copies, and you start measuring, and you decide to measure the spin in the z direction. And now what do you get? Well, we mentioned last time that you don't get an average, or since this is up and this is down, you get 0. You measure the first particle, and whoop, you find it up. Measure the second, up. The third, up. The fourth, down. 5, down. And then you get a series of measurements, and at the end of the 1,000 particles, you find about 495 up and 505 down. About half and half. And if you did with 10,000 particles, maybe it would be closer. Eventually, you find 50% in this state and find 50% in this state. And if you think this is strange, which you probably do, you could be justified, but here would come Einstein along and would say, all this stuff of this superposition is not quite right. You know, you had these 1,000 particles, but actually those 1,000 particles, half of them were with the spin up and half of them were with the spin down. So here you have your 1,000 particles, your quantum state this, but Einstein says, no, let's make an ensemble of 1,000 particles, 500 up, 500 down, and do the same experiment, and the result is going to be the same. So how do you know you really have this, as opposed to somebody has given you 1,000 particles, 500 up, 500 down? How can you tell? And in fact, he would say even more. Whenever Einstein used the word realism to say, if I measure a spin and I find it up, is because before I measured it, the spin was up. It's almost like learning something about an object. If I look at this page and I find it color red, is because before I looked at it, it was red. But then, in quantum mechanics, that doesn't seem to be the case. The state is this mix. And it was this mix before you measure, and after you measure, it's this. So there's no such thing as you learn by doing one measurement what the state of the particle was. So we will not resolve Einstein's paradox completely here, because we would have to learn more about spins, which you will do soon enough. But here is the catch that actually happens, is that if instead of having an ensemble of quantum states, you would have an ensemble of those states that half of them are up and half of them are down, you could now decide to measure the spin of the particle along the x direction. You take these particles and you measure along x. And what you will calculate with quantum mechanics later in this course is that if you measure along x, in these states, you will find all of them to be pointing along plus, up along x. All of them. While on this Einstein ensemble of 50% up and 50% down, you would find 50% up along x and 50% down along x. So there is an experiment that can tell the difference, but you have to look in another direction. And that experiment, of course, can be done, and it's a calculation that can be done, and you can decide whether these quantum states exist, and they really seem to exist. Let's talk now about entanglement. So we talk about entanglement when we have two non-interacting particles. You don't need a strong interaction between particles to produce entanglement. The particles can be totally non-interacting. Suppose particle 1 can be in any of these states, U1, U2, let's assume just U1 and U2, and particle 2 can be in states V1 and V2. And you have these two particles flying around. These are possible states of particle 1 and possible states of particle 2. Now you want to describe the full system, the quantum state of the two particles. States of the two particles. Two particles. Well, it seems reasonable that to describe a state of the two particles, they're not interacting. I should tell you what particle 1 is doing and what particle 2 is doing. Okay, so particle 1 could be doing this, could be U1. And particle 2 could be doing V1. And in a sense, by telling you that, we've said what everything is doing. Particle 1 is doing U1, particle 2 is doing U2. And mathematically, we like to make this look like a state, and we want to write it in a coherent way, and we sort of multiply these two things. But we must say sort of multiply, because a strange multiplication, this, you know, we think of them as vectors or states. So how do you multiply states? So you put something called a tensor product, a little multiplication like this. So you could say, don't worry, it's kind of like a product, and is the way we do it. We don't move things across. We list the first state here, the second state here, and that's a possible state. Now, I could have a different state, because particle 1, in fact, could be doing something a little different. Could be doing alpha 1 u1 plus alpha 2 u2, and maybe particle 2 is doing beta 1 v1 plus beta 2 v2. And this would be all right. I'm telling you what particle 1 is doing, and I'm telling you what particle 2 is doing. And the rules of tensor multiplication, or this kind of multiplication to combine those states, are just like a product, except that, as I said, you never move the states across. So you just distribute. So you have alpha 1, beta 1, the number goes out, u1, v1, that's the first factor, plus alpha 1, beta 2, u1, v2, plus alpha 2, beta 1, u2, v1, plus alpha 2, beta 2, u2, v2. I think I got it right. Let me know. I just multiplied and got the numbers out. The numbers can be moved out across this product. Okay, so that's a state, and that's a superposition of states. So actually, I could try to write a different state now. You see, we're just experimenting, but here is another state, u1, v1, plus u2, v2. Now, this is a state that actually seems different. Why different? Because I don't seem to be able to say that what particle 1 is doing and what particle 2 is doing separately. You see, I can say when particle 1 is doing u1, particle 2 is doing v1. And when particle 1 is doing u2, this is v2. But can I write this as some state of the first particle times some state of the second particle? Well, let's see. Maybe I can, and can write it in this form. This is the most general state that you can say. Particle 1 is doing this, and particle 2 is doing that. So can I do that? Well, I can compare these two terms with those, and I conclude that alpha 1, beta 1 must be 1. Alpha 2, beta 2 must be also 1. But no cross products exist, so alpha 1, beta 2 must be 0, and alpha 2, beta 1 must be 0. And that's a problem because either alpha 1 is 0, which is inconsistent, or beta 2 is 0, which is inconsistent with that. So no, this state is unfactorizable. It's a funny state in which you cannot say that this quantum state can be described by telling what the first particle is doing and what the second particle is doing. What the first particle is doing depends on the second, and what the second is doing depends on the first. This is an entangled state. And then we can build entangled states, and are very strange states. So with two particles with spins, for example, we can build an entangled state of two spin 1/2 particles. And this state could look like this. The first particle is up along Z, and the second particle is down along Z, plus a particle that is down along Z for the first particle, but the second is up along Z. And these are two spin 1/2 particles, and in the usual notation, these experiments in quantum mechanics, in black hole physics, people speak of Alice and Bob. Alice has one particle, Bob has the other particle. Maybe Alice is in the moon and has her electron, and Bob is on Earth and has his electron, and the two electrons, one in the Earth and in the moon, are in this state. So then we say that Alice and Bob share an entangled pair. And all kinds of strange things happen. People can do those things in the lab, not quite one in the Earth and one in the moon, but one photon at one place and another photon entangled with it at 100 kilometers away. That's pretty doable. And they are in this funny state in which their properties are correlated in surprising ways. So what happens here? Suppose Alice goes, or let's say Bob, goes along and measures his spin, and he finds his spin down. So you look here, here is down for Bob. So at this moment, the whole state collapses into this, because up with Bob didn't get realized. So once Bob measures and he finds down, the whole state goes into this. So if Alice on the moon or in another galaxy at that instant looks at her spin, she will find it up before light has had time to get there. Instantaneously, it will go into this state. People were sure somehow this violates special relativity. It doesn't. You somehow, when you think about this carefully, you can't quite send information, but the collapse is instantaneous in quantum mechanics. Somehow Bob and Alice cannot communicate information by sharing this entangled pair. But it's an interesting thing why it cannot happen. Einstein again objected to this, and he said, this is a fake thing. You guys are going to share, and now, of course, they have to share many entangled pairs to do experiments, so maybe 1,000 entangled pairs. And Einstein would say, no, that's not what's happening. What's happening is that some of your entangled pairs are this. That is, Alice, Bob is down, Alice is up. Some of them are this. And there's no such thing as this entanglement. And indeed, if you measure and you find down, she will find up. And if you measure and you find up, she will find down. And there's nothing too mysterious here. But then came John Bell in 1964 and discovered these Bell inequalities that demonstrated that if Alice and Bob can measure in 3 different directions, they will find correlations that are impossible to explain with classical physics. It took a lot of originality for Bell to discover this, that you have to measure in 3 directions. And therefore, the kind of correlations that appear in entangled states are very subtle and pretty difficult to disentangle. So that's why entanglement is a very peculiar subject. People think about it a lot because it's very mysterious. It somehow violates classical notions, but in a very subtle way. Mach-Zehnder interferometers. And we have a beam splitter, and the beam coming in, it splits into 2, a mirror, another mirror. The beams are recombined into another beam splitter, and then 2 beams come out, one into a detector D0 and a detector D1. We could put here any kind of devices in between. We could put a little piece of glass, which is a phase shifter. We'll discuss it later. But our story is a story of a photon coming in and somehow living through the interferometer. And we want to describe this photon in quantum mechanics, and we know that the way to describe it is through a wave function. But this photon can live in either of 2 beams. If a photon was in 1 beam, I could have a number that tells me the probability to be in that beam. But now it can be in either of 2 beams. Therefore, I will use 2 numbers, and it seems reasonable to put them in a column vector. 2 complex numbers that give me the probability amplitudes for this photon to be somewhere. So you could say, oh, look here. What is the probability that we'll find this photon over here? Well, it may depend on time. By the time the photon is gone, it's gone. But when it's crossing here, what is the probability? And I have 2 numbers. What is the probability here? Here, 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 here. And in fact, you could even have 1 photon that is coming in through 2 different channels as well. So I have 2 numbers. And I want now to do things in a normalized way. So this will be the probability amplitude to be here. This is the probability amplitude to be down. And therefore, the probability to be in the upper one, you do norm squared. The probability to be in the bottom one, you do norm squared, and you get 1. Must get 1. So if you write 2 numbers, they better satisfy that thing. Otherwise, you're not describing probabilities. Okay, so on the other hand, I may have a state that is like this, alpha. Oh, I'll mention other states. State 1, 0 is a photon in the upper beam. No probability to be in the lower beam. And a state 0, 1 is a photon in the lower beam. So these are states, and indeed, think of superposition, and we have that the state alpha beta you know how to manipulate vectors, can be written as alpha 1, 0, because the number goes in and becomes alpha 0, plus beta 0, 1. So the state alpha beta is a superposition with coefficient alpha of the state in the upper beam plus a superposition with coefficient beta of the state in the lower beam. We also had this little device, which is called the beam shifter of phase delta. If the probability amplitude is alpha to the left of it, it's alpha e to the I delta to the right of it, with delta a real number. So this is a pure phase. And notice that alpha is equal to e to the I delta. The norm of a complex number doesn't change when you multiply it by a phase. The norm of a complex number times a phase is the norm of the complex number times the norm of the phase, and the norm of any phase is 1. So actually, this doesn't absorb the photon, doesn't generate more photons, preserves the probability of having a photon there, but it changes the phase. So how does the beam splitter work, however? This is the first thing we have to model here. So here is the beam splitter. And you could have a beam coming, 1, 0 beam hitting it, so nothing coming from below, and something coming from above, and then it would reflect some and transmit some, and here is a 1, is the 1 of the 1, 0, and here's an S and a T, which is to mean that this beam splitter takes the 1, 0 photon and makes it into an ST photon, because it produces a beam with S up and T down. On the other hand, that same beam splitter, now we don't know what those numbers S and T are. That's part of designing a beam splitter. You can ask the engineer what are S and T for the beam splitter, but we are going to figure out what are the constraints, because no engineer would be able to make a beam splitter with arbitrary S and T. In particular, you already see that if a photon comes in, probability conservation, there must still be a photon. You need that S squared plus T squared is equal to 1, because that's a photon state. Now, you may also have a photon coming from below and giving you a UV, so this would be a 0, 1 photon, giving you a UV, and therefore we would say that 0, 1 gives you UV, and you would have U plus V norm squared is equal to 1. So we need apparently 4 numbers to characterize the beam splitter. And let's see how we can do that. Well, why do we need really 4 numbers? Because of linearity. So let's explore that a little more clearly. And suppose that I ask you, okay, so what happens to an alpha beta state, if it enters the beam splitter? What goes out? Well, the alpha beta state, as you know, is alpha 1, 0 plus beta 0, 1. And now we can use our rules. Well, this state, the beam splitter, is a linear device, so it will give you alpha times what it makes out of the 1, 0. But out of the 1, 0 gives you ST. And the beta times 0, 1 will give you beta UV. So this is alpha S plus beta U times alpha T plus beta V. And I can write this actually as alpha beta times the matrix SUTV. And you get a very nice thing, that the effect of the beam splitter on any photon state alpha beta is to multiply it by this matrix SUTV. So this is the beam splitter. The beam splitter acts on any photon state, and out comes the matrix times the photon state. This is matrix action, something that is going to be pretty important for us. So, how do we get those numbers? After all, the beam splitter is now determined by these 4 numbers, and we don't have enough information. So the manufacturer can tell you that maybe you bought a balanced beam splitter, which means that if you have a beam, half of the intensity goes through, half of the intensity gets reflected. That's a balanced beam splitter. That simplifies things, because the intensity here, the probability to get this particle must be the same as that. So each norm squared must be equal to 1/2 if you have a balanced beam splitter.